We have three products. One is a retractable flood wall system, one is a surface-mounted flood wall system, and one is an interesting weir wall system that's attached to a detention basin. So this is our first product we'd like to present to you, and this will have Risto Salo, who is our chief engineer, mechanical engineer, describe the elements of the system, and then we have a prepared video that he'll continue on. What you're seeing on the screen is a SolidWorks model that he'll go into detail with. And then after the prepared video, Rick Ellman, who is a geotechnical and structural engineer, will talk about the foundations and the overturning moments to give everybody a general idea of how the retractable flood wall system has been designed and how it works. Risto, please take the screen.
This is the SolidWorks model of a simple retractable flood wall system. So this is just to orient yourself. This would be ground level here, and this is all below ground at this point. And the way the system works is that it extends up like this to create an additional wall. So this is our threat side. So the water pressure would be up against this wall, and there would be a whole array of these mounted in the ground. So you can see how this would work. And before we start designing anything, we'd have to obviously have some design standards that we would work off of. The FEMA 55 Coastal Flood Manual, the ASC 7 design loads and local building codes. And then also we would need to know a couple of other things, is the flood height, which would be our hydrostatic force. How much flood are we trying to protect on this side? If there's any, this is a coastal location and we have wave action, we have hydrodynamic loading against this wall. If it's against a river, we may have water current. And in some areas of the United States, particularly the southeast, we have wind loads when this is in the extended position, especially in places that are prone to hurricanes. So once we have all those, we can design a system with a foundation and an extending flood wall. This one is shown as 5 feet wide and 5 feet tall. It's a fairly small wall, but it's an easy one to show the major elements. First major element is the foundation, which goes below grade. So this is our foundation. All this is surface area up here at the top would be surface. And then this is a precast concrete and rebar unit, and they get mounted side by side all the way down to create a flood wall system. Some of the key elements here are the vertical guides that guide the wall. There's 4 places here. This is the winch that lifts the wall in place. And there's some cable terminations, and I'll talk to those in a little bit here. So there's many different ways to create the foundation. This is a single precast unit. Larger units may be split in half here as a front and back, and then pinned or tension rod together. Then there's other ways is to split it horizontally and make it a stacked unit with vertical tension ties to create a uniform structure. The other major element obviously is the wall itself. So this is our wall. And this is again a precast concrete unit with inserts so that we can attach all of the elements to it. So the vertical seals on this side, pockets on this side, so that when the 2 walls are next to each other, the one wall seal goes interlocks into the pocket of the adjacent wall. There's a top plate here that protects the horizontal seals, and it could be a drive-over cover, depending on what the load conditions are. We have an up block, which prevents the wall from accidentally retracting when it's in the up position in case of a power failure or a cable failure. The wall would always stay in the up position. We have guide wheels, 4 on the front, 4 on the back. These are shown as V-groove wheels. There's other higher load applications would have different roller assemblies that would carry the load. So this is the up block, and this swings out like this when it goes to position. This is a trigger that allows it to swing out, and then when you retract it, you can lock it back into position and it's ready to use for the next time. So when the wall raises, this swings out automatically. So there's no mechanism other than spring loaded to extend it. Okay, there we go. So those are there. So these, the other features here are, these are horizontal seals that prevent water from flowing down between the wall and the foundation. This is our primary seal on the front, secondary seal on the back to keep dirt and any water from flowing around the wall and then back to the dry side. This would be our dry side on this side. The winch in the cover here. Here's our winch. It's a cable-driven winch. Cable like this. It's down to the down position. Yeah. So the cable comes off of a winch drum here over a sheave and around the bottom sheaves here and terminates on the other side. So this is called a double purchase system. So the load on the cable is reduced by half because half the wall load is hanging on this side and half of it is on the winch. It also keeps the winch size reasonable. So this is the gearbox, double gearbox and electric motor. On the top of this, we have a feature, auxiliary input, where we can actually drive this. If you have a power failure, you can put an auxiliary drive here and drive the gearbox to the up, or drive the wall to the up position by driving through the gearbox without any power applied. There's a small surface drain here from the dry side that drains back down into the sump. Show it back in here. So when the wall is in the down position here, it rests on the foundation at the bottom here. So if this is a drive over cover or has a load on it, the load here doesn't hang on the horizontal seals or on the winch. It actually is bearing against the foundation down at the bottom. So this wall is in compression at that point. There's a plumbing feature here, which we call the sparger pipe. It's a horizontal pipe with holes in it. And the use is to clean out any silt or debris that gets into here. We pump water into here. These are continuous. Pump water into here, and the water comes out of the small holes here on the side and churns up the any water that's left in this cavity here. And once it's in suspension, we change the valves out and we use a pump to suck all the water back out again. So that is a way to clean this, fairly clean the sump here without actually having to do it manually. So it's an automatic system. A couple of electrical features that we have. There would obviously be a motor drive that drives the motor. There would be one for each wall. And then there would be limit switches showing when the wall is in the up position and down position to control the winch. And then there in the sump here, we would have a water level sensor and a turbidity sensor. So we know how much water is accumulated in here and how dirty the water really is. And that gives us some logic on when to pump water out and when to pump water in. So this is our flood wall system. And now we'll continue. There's a video that describes how a lot of this is used in the application. And let me go to the video. So this is a standalone, different version of the winch. This is the stacked version of the foundation, as we talked about earlier, with the tension rods. This is showing the assembly of the foundation. So we're putting in the vertical guides, the lifting points, the winch motor. Here's the cables and the seals. The same thing with the wall itself. This is showing the stacked version with the tension rods. And spring-loaded up blocks. Here's our guides being installed and the lower shivs. And now we have and the gasket retainers. The vertical seals or vertical gaskets, and this is showing all together now. an assembly. So animation showing how the cables retract raise the wall by retracting. Wall showing horizontal, so you can see through the wall and you see the guides on the opposite side. Cable terminations are shown there, highlighted. So the design speed generally is about 1 inch per second, so a 5-foot wall would come up in that 60-second time. Here's that same wall that I showed you earlier in the SolidWorks model, shown with a temporary test tank behind it. This would be used for developing and testing the seals and the uplocks. One of the other things we can do with this is we can show this is a powered auger, and that this would attach to the auxiliary drive. Here's a retrofit installation at a levee. So at the ground of the levee, we attach the RSA flood wall system, and it would protect the land beyond the levee then from excessive flooding. You can see the walls don't have to move in complete sequence. You can move multiples at the same time. Here's a design for a operable floodgate where we have a fixed flood wall and we're trying to close off a roadway. This is a non-powered system, so we're actually have to move the walls into position and then they seal up the opening. Just showing the flooding of that. It takes a lot of it, because it's a manual system, it takes some equipment and some people to move it into location. This is the same opening using the retractable flood wall system with end walls at each end. So this would be minimal people to operate this. You could close off the roadway just by raising the flood walls. Here's some of the key elements again. This is showing a pattern of 4 flood walls across the roadway. This is the flood side. You can see the water pressure would be up on the walls on that side. And the same 4 panels from the dry side or the safe side. The uplocks are shown extended. And then there's a discharge pump, which I talked about earlier in the SolidWorks model. I have some better images here. Kind of an exploded view of how this is assembled. This is a foundation that's a front and rear assembly. There's a detail of just the winch. You can see how the cables wrap around the lower shivs and come up and terminate on the opposite side. Linear guides. These are Hillman rollers, which are heavy duty guide rollers, and they run on a steel track. Here's our swing out uplocks. And the horizontal gaskets or horizontal seals laid into location, and the vertical seals. And all of those seals are plain rubber material. They don't have really a profile, so they're easily sourced and easily replaced. Here's our pump system, what we were using with the Sparger system. So this kind of runs through some of the ways of using that system. So there's the Sparger pipe, and the valve actuator, vertical pump, and this is our drain back to the wet side. So we can also take drain water from. So this is the water. If we have any seepage through the seals, it falls into this cavity down here where the Sparger pipe was. It gets pumped out through the pump and out through the wet side discharge. There's a check valve here to keep water from flowing back through the system. There's a drain here on the safe side that keeps water from pooling on top of our unit, and it drains back into that same sump and gets discharged the same way. So this is if there's additional site drains that we need to drain, they could drain into this system and get pushed out to the wet side also. So these would be surface drains that are part of the system. Here's showing the clean out system. We're showing the sediment there. We're pumping water through the sparger pipe to get the sediment into suspension. And then we start pulling, by running the pump, we can pull the dirty water back out of the sump and discharge it out through the exit. Here's an installation that was attached to an existing seawall. The seawall wasn't tall enough really to prevent flooding, so it was going to be a retrofit to an existing seawall area. This shows the flooding before the flood wall extension was added. So here's the flood wall system attached to the existing base structure, tied together, and Rick Elman will show a little bit more of this detail later in his presentation. So this is our seawall extension, basically. It adds some extra height to the height of the seawall without actually reconstructing the seawall. Well, water returns to the normal level, and we retract the seawall to give you a flat surface again. So it doesn't impede any of the pedestrian access to this area. Here's some variations on the flood wall system. We can obviously go around a shallow angle by creating a special wall that would work around that area. Here's showing this angled wall. We could go through changes of elevation by stepping the wall along the elevation, and there would be a special, what we call a monument here at each location, so that we can mount the walls without having them. The seals would be maintain a good seal in between. The sparger pipe system would step up along that edge. There's the locations where we'd have underground utilities, like storm drains, where we'd have to pass that through. We created a special monument then that would be poured around that pipe or duct or pipe without having to cut the pipe. This is for smaller pass-throughs. We can have a similar kind of event. Here's a mirrored monument shown in the upper left there, where we could create two precast sandwich pieces to wrap around the pipe without actually having to pour it in place. Places where we have these monuments, they're obviously going to be exposed all the time. So in certain locations, that would probably not be preferable to have that. So there are ways to reduce that by removing the upper portion of that and attaching it first and then raising the flood walls. So that would be a separate operation. The next step beyond that then is to have that and have a raising gate, basically a hinged flat plate that would create that wall section, but fold flat for access. Here's a little video showing how that works. This is the storm drain pipe showing here, and we have the monument around that, and then this would be the walls raising up on either side of that, and then a large steel ceiling plate, basically, that's either hydraulically or electrically operated, that would raise up then and cover up that opening where we couldn't have a retractable flood wall. So that would seal against the existing, the raised up walls. And in the retracted position, this would be then flush to the ground and allow pedestrian access. There's a patent, a copy of the patent that RSA has for the retractable flood wall. So a different variation of this without, so this would be a system where we could have modify an existing T-wall or I-wall, where we could add the RSA system attached directly to the back of a T-type inverted T flood wall or a levee wall. And we could increase the height without having to rebuild the wall. And also on the right there, it shows it attached to the back of an existing eye wall the same way. So a variation of the flood wall is to not have it powered at all with the winches, but actually lift them into location. So this shows some patent images of a dedicated crane basically lifting the flood walls into position. This is our video of an existing inverted T-wall and showing the retrofit of the RSA flood wall attached to that. So here you can see the flood wall was attached into the existing T-wall, an additional foundation put in for the overturning moments, and it's showing a crane lifting each one of the walls into position. So in this case, the wall comes to the up position and the up blocks lock it into position so it stays there when the crane rolls away to the next wall. The wall stays in the up position automatically. We have the pump system, just like we did before for the sparger pipe, which is underneath, and then the piping would run under the wall and back out to the wet side. So this would continue then all the way down. Just basically move from one panel to the next, just lift them up into location and move on to the next one. Yeah, so to lower it, you retract the up blocks and you lower it back into the wall, and you would do it in the reverse order. So it is showing what the foundation walls transparent so that you can see some of the features inside. There's no winch, so it's just basically the guides and the up blocks are the only features in there, and the seals. So it shows the full row of panels in the up position. same image from the wet side. Again, you can see the transparency, you can see the seals, the guides, and showing a little sequence of the flooding running over the top of the existing T-wall, and then additional video of the walls extended, holding back the flood. It's a slightly different application where there's the soil on the dry side is actually higher than the other side. And this would be a typical. So this is a example of a levee protected community. We've got a river or body of water here, and the RSA wall is attached to the edge of the roadway here. And once you raise that up, it makes the levee higher, and then it will protect the community behind it from floodwater. In areas where the levee is localized, but floodwater could continue all the way around, this is a system called a ring levee, where you can basically protect the entire perimeter of a community or a industrial section, and then in order to avoid getting water coming in from the backside. So this shows the wall at the top of the levee being raised up by the crane. You see the cutaway there shows the foundation down inside the levee. Shows the system in the up position. Some of the non-powered applications, you can come up with different ways to power the winch without having electrical power. Here's a slide showing another application where we have the extending flood wall, but we also have an energy absorbing cladding on one side for a blast proof. Now here's a typical application for a beach location. Happens to be Miami Beach location where we got flood water coming up the beach and into the buildings. This is the RSA system installed on the beach, not on the boardwalk. So it protects all the vegetation and the boardwalk without being interfering with any of the structure there. So this is actually buried in the beach and raises up from there.
I'm now going to speak about some applications that we developed with the RSA team for the movable wall affixed to a existing bulkhead platform. This is in Battery Park City, the southern end of Manhattan, and facing the Hudson River, where certainly experienced some extreme flooding after Sandy and the need for some kind of flood protection. So on the screen, you see a plan view of our bulkhead platform, and below is a little partial plan showing the framing for that platform and then the RSA system as it would be integrated to it. Basically, this particular structure is it's a pile-supported concrete low-level relieving platform, and the RSA movable wall system is affixed to the back end of it. And you can see we basically developed the requirements to resist all of the forces that are applied to the system, and develop the internal structure for resisting the forces from the flood, as well as affixing the structure to the existing structure. This is just a similar view of that as well. So just to get into, not to get into the weeds, but each of the components are designed for the applicable forces and the requirements for the concrete strength, reinforcing demand to provide all of the bending and shear resistance that each of these components need to develop. This slide shows just basically the applied forces. So, there are driving forces that include hydrostatic pressure, hydrodynamic pressure, and impact. Basically, in this particular situation, there were no waves or breaking waves to consider. And then we have also the wind, and all of these forces are then applied, and the requirements for global stability and overturning resistance are evaluated. This was a slide showing the design of the actual foundation structure and the requirements for the reinforcement demands for both flexure, shear, and axial. And similarly, the reinforcement demands for the attachment of the structure and checks for, uplift and overturning and the physical forces that need to be transmitted to the existing structure and to make sure it can resist those forces. And then finally, the design of the wall panel itself and the reinforcement demand on that. Subsequently, we also did a similar investigation for the Miami Beach project that Risto mentioned earlier in the video. And this is now a system where this requires an independent foundation. So there's no existing structure to support the system. In this case, in this beach environment, the movable wall system is built to whatever existing grade there is, whether that's the boardwalk elevation, sand dune elevation, whatever, and it's typically buried and is raised quite a bit, right? So these dunes are already somewhat high level, high elevation areas. Our structure extends below grade, and then there are independent foundation elements. In this case, this was pipe piles, and they're designed for both the uplift and compression and forces that are required to resist the flood. This is another view of how that might be configured. And this kind of just shows the loading again and incremental loadings, where we have hydrostatic loading, hydrodynamic loading, impact. Now here we're in a coastal zone environment, so we have waves, and we have a breaking wave force, which is usually the driver of the larger of the forces. They're usually very significant. And then these are the forces at the surface, and then we also have soil pressures that are acting on it. We have buoyancy that wants to tend to lift the thing, and we have wind load. So all of these forces are taken independently and considered collectively combined on the overall structure. And then here we're designing our pile designs. Here we're talking about overturning stability and showing that the structure is going to satisfy requirements for overturning stability. These are the layout of the piles and pile forces and the forces that are acting on our wall structure. This is the analysis of the piles using a software called L-Pile, which just shows how the piles are resisting bending moment and that they can be developed in the soils that we have. And to that point, I'll just say that with any of these projects, obviously the geotechnical conditions vary, and all of them will require an independent geotechnical investigation and a proper design of the foundation system that makes the most sense, as well as making sure there are no piping issues, underground flows that could bypass the wall. And that's what Muser Rutledge adds to the RSA team with regard to this movable wall system.